Dear learners, welcome to the course Antennas and Microwave Engineering. In this video, I will be explaining the characteristics of Gunn Diode, working principle of Gunn Diode, and the applications of Gunn Diode. This is the outline of my presentation. Gunn Diode is a two-terminal semiconductor diode with a negative resistance property used in very high frequency. Gunn effect diodes are named after J.B. Gunn, who in 1963 discovered a periodic fluctuations of current passing through the N-type gallium arsenide specimen when the applied voltage exceeded a certain critical value. Gunn diode is based on Gunn effect or transferred electron effect. It is also called as transferred electron device. In a separate video, I have explained the comparison between microwave transistors and the transferred electron device. This is the specimen of gallium arsenide diode. In later years, the limited space charge accumulation diodes, that is LSA diode, and the indium phosphide INP diode were also successfully developed. These are bulk devices in the sense that microwave amplification and oscillation are derived from the bulk negative resistance property of uniform semiconductors. So this figure, it illustrates field versus drift velocity, and this right hand side, this figure, it illustrates current waveform. It represents the periodic fluctuations in the current waveform when the applied voltage is greater than the critical voltage. So in the gallium arsenide specimen, this fluctuation is in the form of a periodic oscillations superimposed upon the pulse current. The frequency of oscillation is determined mainly by the specimen, not by the external circuit. The period of oscillation was inversely proportional to the specimen length and closely equal to the transit time of electron between the electrodes. From Gunn's observation, the carrier drift velocity is linearly increased from 0 to maximum when the electric field is varied from 0 to a threshold value. When the electric field is beyond the threshold value of 3000 volt per centimeter for the N-type gallium arsenide specimen, the drift velocity is decreased and the diode exhibits negative resistance, which is illustrated in this figure. After reaching the threshold value, the drift velocity starts decreasing. It exhibits a negative resistance property. Ridley, Watkins, Hilsum theory, RWH theory. RWH theory is the differential negative resistance developed in a bulk solid state third and fifth compound when either a voltage or a current is applied to the terminals of the sample. Generally, there are two modes of negative resistance device. It may be voltage controlled and current controlled. Figure A illustrates the characteristics of voltage controlled mode and figure B represents current controlled mode device. For the voltage controlled mode, the current density can be multi-valued, but in the case of current controlled mode, the voltage can be a multi-valued. So in the case of voltage controlled mode, high field domain are formed, separating two low field regions. This figure illustrates the high field domain, and in the case of the current controlled mode, it separates the sample, results in high current filaments running along the field directly. It represents a high current filament. Generally, the characteristics curve is in the N shape. In the case of voltage controlled mode, it is in the shape of N. But here, in the current controlled mode, the characteristic curve is in the shape of S. Next, we are going to talk about two-valley model theory. This two-valley model theory is also known as RWH theory. It is generally based on population inversion principle. For an n-type gallium arsenide energy band model under equilibrium, when electric field E is less than or equal to threshold value, that means 3.3 kilovolts per centimeter, the electrons are transferred from lower valley to upper valley of conduction band, in which they are much less mobility, and thus the current reduces and the device offers a negative resistance. This is also known as transferred electron effect. This figure shows the two-valley model of n-type gallium arsenide. So here, electron densities in the lower and upper valley remains the same under an equilibrium condition when E less than EL. When the applied electric field is lower than the electric field of the lower valley, no energy will transfer to the upper valley. This is the first case. And when the applied electric field is higher than that of the lower valley and lower than that of the upper valley, that is between the range EL and N and EU, upper and lower valley range, the energy electrons will begin to transfer to the upper valley. The second figure B. When the electric field is higher than that of the upper valley, all electrons will transfer to upper valley. If electron densities in the lower and upper valleys are NL plus NU, the conductivity of the n-type gallium arsenide is given by sigma is equal to E into mu L NL plus mu U N U. L and U, it represents the lower valley and upper valley. E is the charge of an electron and mu is the mobility of the electron. It represents mobility of electron in the lower valley, mu L. Mu U is the mobility of electron in upper valley. Next, we are going to derive the condition for negative resistance. Now, differentiating equation with respect to E, it gives d sigma by d E. We are differentiating the equation for conductivity with respect to electric field. If the total electron density is given by N is equal to NL plus NU, and it is assumed that mu L and mu U are proportional to EP, where P is the constant, then dN by dE is equal to 0. Therefore, dNL by dE is equal to minus dNu by dE. Now we substitute the equations. It results as per Ohm's law, current density J is equal to sigma E. Then we differentiate current density with respect to electric field. We will get the expression 1 by sigma dJ by dE is equal to 1 plus d sigma by dE by sigma by E. For negative resistance, current density must decrease with increasing E, or the ratio of dJ by dE must be negative. So therefore, substituting the equation with F is equal to NU by NL results in, and this is the condition for negative resistance. The field exponent P is a function of the scattering mechanism and it should be negative and large. Next, we are going to talk about the various modes of operation. Depending on the material parameters and the operating conditions, various modes have been developed. The modes are Gunn oscillator mode or transit time mode, stable amplification mode, LSA oscillation mode, bias circuit oscillation mode. These are the various modes of operation of Gunn diode. We will discuss one by one. First type is Gunn oscillation mode. Operating frequency and length L is equal to 10 power 7 centimeter per second, and doping N0 the length L much greater than 10 power 12 per centimeter square. Generally, it ranges from 10 power 12 per centimeter square to 10 power 14 per centimeter square. The normal Gunn domain mode, that is Gunn oscillation mode, is operated with the electric field greater than the threshold field. That means E is greater than ETH. There are three possible domain modes for the Gunn oscillation mode. These modes are transit time domain mode, delayed domain mode, quenched domain mode. These are illustrated in figure A, B and C respectively. For the transit time domain mode, when the electron drift velocity is equal to the sustaining velocity, the high field domain is stable. The electron drift velocity is equal to the sustaining velocity. The oscillation period is equal to the transit time. Here we represent this is the rho naught is equal to T, transit time. The efficiency is below 10% because the current is collected only when the domain arrives at the anode. Second mode, the figure B illustrates the delayed domain mode. Generally, the FL product, this ranges from 10 power 6 cm per second to the 10 power 7 cm per second. When the transit time is chosen so that the domain is collected while E is less than ETH, a new domain cannot form until the field rises above the threshold again. The oscillation field is greater than the transit time, that is tau naught greater than tau T. This delay mode is called inhibited mode. The efficiency is above 20%. Here you note down this tau naught greater than tau T transit time. Third one is quenched domain mode. That means the FL is greater than 2 into 10 power 7 cm per second. In this mode, if the bias field drops below the sustaining field ES during the negative half cycle, the domain collapses before it reaches the anode. When the bias field swings back above threshold, a new domain is nucleated and the process repeats. Hence, in this mode, the domain quenched before reaches the anode. Therefore, the oscillation occurred at the frequency of resonant circuit rather than at the transit time frequency. The resonant frequency of the circuit is several times the transit time frequency. The efficiency is 13%. Next mode is stable amplification mode. The operating frequency F and the length FL product is equal to 10 power 7 cm per second, and the doping N0 and the length L is equal to 10 power 11 to 10 power 12 per centimeter square. And another mode of operation is LSA Oscillation Mode. This is the most important mode of operation for Gunn oscillator, as this mode gives high power. In this mode, the domain is not allowed to form at all. The frequency and RF voltage are so chosen that the domain do not have sufficient time to form while the field is above the threshold. As a result, most of the domains are maintained in the negative conductance. Negative conductance state during a large part of the voltage cycle. The LSA mode yields high power and high efficiency. that is about 20%. So therefore, the output power of the oscillator in LSA mode is P is equal to eta I naught V naught. Eta is the conversion parameter of material, I naught is the operating current, V naught is the operating voltage. There are some limitations in LSA mode. LSA mode is very sensitive to load. LSA mode is sensitive to operating temperature. Variation in doping concentration affects frequency stability. These are some of the limitations of LSA mode. Another mode is bias circuit oscillation mode. This mode occurs only with either Gunn or LSA oscillation, and it is usually at the region where the product of frequency times length is too small to appear in the figure. When FL is very small, the device is biased at the threshold. The oscillation frequency can be obtained in the range of 1 kHz to 100 MHz. For an N-type gallium arsenide diode, the criteria for classifying the modes of operation is N0L greater than epsilon Vd by E mu N, where epsilon is the semiconductor dielectric permittivity, Vd is the electron drift velocity, mu N is the electron mobility, and N0 is doping concentration, and E is charge on electron. So this figure illustrates the structure of Gunn diode. These slices of gallium arsenide cannot be used directly in the waveguides, thus there is a need of encapsulation. Even though it is a bulk device, it can be used as a diode because it has got two leads for the external connection. If voltage or electric field at a low level is applied to the gallium arsenide, initially the current will increase with the rise in the voltage. When the diode voltage exceeds a certain threshold value, a high electric field is produced across the active region, and the electrons are excited from the initial lower value to the higher value. If the rate at which electrons are transferred very high, the current will decrease with increase in voltage, resulting in equivalent negative resistance effect. So this figure, it illustrates the negative resistance characteristics of gallium arsenide diode. Here I have listed a few of the characteristics of Gunn diode. Efficiency is 2%, pulse to power is 5 watts for the frequency range of 5 to 12 GHz. TW power, continuous wave power is 25 milliwatts to 250 milliwatts. 100 milliwatts at the frequency range of 18 to 26.5 GHz. 40 milliwatts at 26.5 to 40 GHz. It typically uses 10 volt supply and a current of 140 milliamps and has a power dissipation of 1 watts. These are the general characteristics of Gunn diode. This figure illustrates the electrical equivalent circuit of a Gunn diode, where this Rj and Cj are the diode resistance and diode capacitance, where Rs is the total resistance of leads, ohmic contacts, bulk resistance of diode. Lp, Cp are the package inductance and capacitance respectively. Gunn diode oscillator circuit. Gunn diode can be used for both oscillation and amplification. Here, the Gunn device is located under a post in the rectangular waveguide. The cavity is resonated at the desired frequency by adjusting this short circuit. So here, tuning screw is provided. Gunn device is placed in the post. The degree of coupling to the external waveguide is adjusted by changing the window opening in the inductive diaphragm located at the front end cavity. The top of the waveguide is insulated from the waveguide. The DC bias voltage approximately 12 volt is applied to the post. There is sufficient capacity between the post and the surrounding waveguide to provide an adequate low impedance RF bypass capacitance, and the RF current does not flow through the bias voltage supply. Fine tuning of the cavity can be obtained by means of a tuning screw. So this is the another arrangement of Gunn oscillator. So in this cavity, the high impedance of waveguide is transferred into the low impedance at location of the Gunn device by means of quarter wave transformer. The cavity frequency can be adjusted by changing the location of the short circuit. A tuning screw can be used for fine tuning of the cavity. So in this figure, this is the second method. The power output of the Gunn diode oscillator is in the range of a few watts for CW operation at biasing values 10 volt and 1 amps at 30 to 40 GHz. A frequency tuning range of 2% can be achieved. For pulsed operation, peak power are typically 100 to 200 watts. The output power of Gunn diode is limited by the difficulty of heating dissipation from the small chip. The advantages of small size, ruggedness and low cost are some of the advantages of Gunn oscillator circuit. Gunn diode can also be used as an amplifier. This figure illustrates Gunn diode as an amplifier circuit. Gunn diode with negative resistance characteristics can be used as an amplifier. When RF signal is applied to the Gunn oscillator, amplification of the signal occurs, provided that the signal frequency is low enough to allow the space charge in the domain to readjust itself. There is critical value of FL, that means frequency into length, product of frequency and length, above which the device will not amplify. Below this frequency limit, the sample presents an impedance with a negative real part that can be utilized for amplification. In contrast to the stable amplification, the Gunn effect diode must oscillate at the transit time frequency while it is amplifying at some other frequency. The value of N0 N, doping concentration and length, must be larger than 10 to 12 cm squared in order to establish traveling domain oscillations. Hence, substantially large output power can be obtained. Because of the presence of the high field domain, this amplifier is called a traveling domain amplifier. So therefore, Gunn diode can be used as an oscillator and also used as an amplifier. Here I have listed some of the applications of Gunn diode. Gunn diodes are used as low and medium power oscillators in microwave receivers. Gunn diodes are used in parametric amplifiers as pump source and also used in radar transmitters and also used in broadband microwave amplifiers. Gunn diode can also be used in fast combination and sequential logic circuits. I hope you could understand the characteristics of Gunn diode and applications of Gunn diode very well. Thank you.